Okay, here we have web assigned 9C, problem number 6. This is Gauss's law. A solid conducting sphere of radius 2 centimeters is a charge of 8.9 10⁻⁶ coulombs. The conducting sphere shell of inner radius 4 centimeters and outer radius 5 centimeters, concentric with a solid sphere, and is a charge of -2.46. Find the electric field, the following radar from the center of this charge configuration. Okay, so I already went ahead and drew this picture just to help us visualize what we're actually dealing with here. So part A is R equals 1 centimeter. So, in using Gauss's law, we're going to have to draw our little Gaussian shape. So this is about 1 centimeter. It's my circle. But immediately, if we caught on in this sentence, this conducting sphere, and Gauss law deals with the electric field, and we know that inside of a conducting sphere, the electric field is 0 because all the charge is on the outside. There's nothing on the inside, nothing's passing through on the inside, therefore it is 0. So the magnitude is 0, and therefore that means the direction is 0. Now, our second one, let me just get rid of our first shape. Our second one asks for 3 centimeters. So now this is going to be outside. It's going to be this little, it's going to be in this area now. So as you can see, it's obviously not 0. We're not inside of this conducting sphere anymore, but we're also not touching or within this did it just say solid sphere? It just says solid sphere. I thought it might have said, yeah, anyways, okay. Now, this is using our shape, we then have to, figure out what the field is. So this is Gauss's law. EA is the cumulative of epsilon naught, E being the electric field, A being the area. The charge enclosed is the charge enclosed, and within this sphere we drew, which I'll be showing you, and epsilon naught is our permeability constant. So after drawing this little green circle up here, we can then try and look to figure out the charge that we do have enclosed. And as you can see, all that's enclosed by this circle is the conducting sphere, and that conducting sphere has a charge of 8.9. I want to say micro, but I feel like that's wrong. It's 8.9 times 10⁻⁶ coulombs. So I can just simplify this. So E, electric field, will be then equal to our charge enclosed divided by epsilon naught times our area. E is equal to our charge enclosed over epsilon naught. This epsilon naught, or our area, what's a sphere? Surface area of a sphere is 4 pi r squared. Epsilon naught, and we know that epsilon naught times, or 4 epsilon naught, 4 pi epsilon naught is equal to our constant. And this would be like this. And as you can see, that gives us our equation. That's how we get our equation for our electric field, and then we can just plug in. I'm not going to write out the constant, but I will write out our charge enclosed because it will help to see where everything comes from. And our R squared, now it said we're 3 centimeters from the middle. So it's 0.03, and don't forget about your squared, and that'll come out to this. Remember, our constant is 9 times 10 to the 9th. And you'll get that answer. And then now direction is outward, and the purpose for the direction being outward is because we have a positive charge, which means a positive charge is going to repel other positive charges, and our direction of repelling in this sense will be away from the center, which is outwards. Now I'm just going to erase this sphere here and draw our next one. So now we're at 4.5 centimeters. Now we are in, we're like right in here, like inside of it. So now, again, we have to pay attention to our language here. We have a conducting spherical shell. That's the shell that we're inside of. And using the same knowledge we just used from our sphere, we need to apply this here in that inside a conducting metal conducting, I guess I just call it a shell, inside of it, because all of our charge is on the outside, there's nothing going on in the inside, which means the electric field inside would have to be zero, and therefore the direction, well, if there's no field, there's no magnitude, there's no direction, so that has to be zero as well. That definitely didn't make sense to me at first, being that there was this, this whole charge inside of this sphere. Looking back, it seems kind of awkward to even thought of it that way, but being introduced to this, I was convinced that because I had a charge within this circle, that had to mean something towards the field. And I think this C took me maybe 2 or 3 tries before I got the part A right, which was 0, and I was like, oh, wait a minute, we're in another conducting shell of some sort, or conducting a sphere of some sort. I mean, it's gotta be the same thing, right? So it was, and that's how I figured out, inside of conducting materials, the electric field's gotta be 0. Okay, in D, I got this one wrong. I could not figure out why I got this one wrong, and I can guarantee you I got it wrong because I drew my circle the wrong way. And I'm going to draw my circle the right way, my Gaussian, yeah. It needs to look like this. Now we're encompassing the entire system, which means every single charge it gives us, meaning this 8.9 and this 2.46, needs to be taken into consideration to find the electric field of this entire thing. So, how do we find the charge of the whole thing? Well, we just add our charges together. We have a negative and a positive, so we're going to add them together. And I'm not going to... So it's just 8.9 plus this negative 2.46, I understand there, and 10 times negative 6 coulombs. But just to make it a little bit easier, or write a little bit less on here, what's that, 6.54 times 10 negative 6. So that's our total charge of this. Taking into consideration the negative charge of the spherical shell and the positive charge of the inner sphere, because of the circle we draw, we have to take into consideration every single charge in there. And we know the net of this one, and we know the net of this one. We add them together, find the net of the whole thing. And that's how we got here, and this is cool, just to be clear. So then this is our charge enclosed. Charge enclosed by the sphere that we drew. Or the circle, I should say, that we drew around the system. So that then when I go to plug that into our equation, this one right here, or better yet, this one, the one that's simplified, it's E is equal to our constant, which is 9 times 10 to the 9, not negative 9. Was it Newton's 9 meters squared over Coulomb squared, times 10 to the 6 coulombs, and coulombs, because that's a C there. Let me just redraw it. Coulombs. And now it's take into consideration our distance. Now, don't get confused here and do the distance from the conducting spherical shell, which would be 2 centimeters, considering the outer radius is 5 and we're 7 centimeters totally out. It's still from the center of our system, of our, this drawn circle. I guess it's not a perfect circle, but we're still going from right here. This is our center. This is where, this is the midpoint. This is the middle of our system. We're going from that distance. That's our radius. So again, we just use the radius they give us, which is, don't forget to square it. And I don't have to calculate this, but because obviously I didn't get it right up there. 5.84 times 10. Oh wait, no, that's the wrong problem. Oops. And yeah, remember this negative 6 part, because sometimes I'll write it like this, and I won't remember to put the coulombs, or not the coulombs, I won't remember to multiply it by the, or give it back its significant figure, and then my answer is obviously wrong. I guess this should come out to be like 1.201 times 10 to the 7th. I guess I got the 10 to the 7th right, and I wonder what I did wrong. I don't remember what I did wrong, if I'm being quite honest. Yeah, I'm not sure. But and then to find this direction, it's just basically the sign of the charge. So you see we have the negative 2.46 and we have the positive 8.9. Now, if the 8.9 was the one with a negative attached to it and the 2.46 was positive, our field would be inward because it'd be a net negative charge that would want to attract other positive charges. That's the flow of the positive charge. That's direction of the electric field. Electric field is the direction the positive charges would flow. If it's negative in the middle, positive charge is going to flow towards it. If it's positive in the middle, like the sphere on the inside was, charge is going to go outwards. But again, because this 8.9 is positive, it's larger than our negative 2.46. Our net is positive, therefore our direction is still outwards like it was in the middle strip. So, yeah, this problem was, looking back now, is I wish I could go back to these ones. To be honest, I say, have a pretty good understanding. I actually know what my formulas are. It's a lot simpler once you've done it multiple times. This one I can, I know it looks like I did pretty well on it, but I mean, half the answers were 0. That was the easy part, and then I had to figure out, where I go from there. Well, you just kind of imagine, you just kind of draw it like I did here. I drew it on my notes when I was trying it for the first time. Made it a lot simpler just to visualize my Gaussian, this little dotted circles I drew, like what charges are inside, what my charge enclosed is, how that gets into the equation, how that ends up affecting my directions. It's just a whole bunch of little things that once you understand the little parts, then the whole thing becomes that much simpler.